Hey you guys, welcome back to the channel physicssirjee, and here we are in a snippet video from Heat and Thermodynamics detailed course on our physicssirjee app. So before we move on to that snippet and learn something very interesting from the thermal physics and kinetic theory of gases, a small request. I had to put this at the start because students on this particular channel keep enjoying the quality content over a period of last 2-3 years, but tend to somehow forget to like the video. Virtual likes are there because always the content in this particular channel brings a lot of smiles to the students, especially the serious students, but they tend to forget to like the video. So I would request you to like, share and subscribe to the channel in case you are new. So the notification bell icon is something also that I would suggest to hit for the serious students, okay, so that you end up getting the more and more notifications when I become very active. So the activity on this particular channel would be directly related to the likes, because that's how the YouTube algorithm works. That's the first point. The second important thing, what you are going to see is a snippet. That means it's a part of a bigger lecture cut out strategically from a detailed course. Okay, so there will be some slides before that which would have explained the phenomena, and there will be slides after that which would continue the explanation. So it has been cut out so that you can get a glimpse into the concept. You can watch it as a standalone part also. I have made sure that the cut is done in such a way that students with simple knowledge of kinetic theory of gases and how not to use Maxwellian distribution will completely understand the video. Okay, and also watch the video till the end, because at the end of the video I would be providing you the announcement about the next problem contest, and I would be requiring some advice in the comments section below once you listen to the part at the end. Before we move on very quickly, so this particular snippet you're going to watch is taken from the detailed course, both for the 2025 aspirants, where batch 1 and batch 2 are already announced. You can check out the you can check out the courses links from the pinned comment below or in the description. Also the batch 1 and batch 2 of the successful 2024 detailed course that has been launched. So without much further ado, let's move into the snippet, and also please wait for me for the announcement at the end. So I hope you have given it enough time to read the question as I suggested and gave it an attempt. So I'll go ahead with the discussion of the solution now. So this particular problem, we need to understand it's like a very good tool to understand what we have done in the previous slides. We tried to realize the kinetic theory of gases, arrived at VRMS formula, and then discussed the Maxwellian distribution of velocities, tried to understand how the Maxwellian distribution came about, and solved some hypothetical distribution function problems also, and then we arrived at this particular place. So this problem, when we are dealing with in this sequence of slides in the lecture or sequence of understanding in the lecture, this should enhance our understanding of whatever we did in the previous slides, both the theory and the problem solving part. So with that spirit, I took up the problem here in our course. So the question is very simple, right? It's from the famous book Pathfinder. Speed distribution of molecules of an ideal monatomic gas. So reading the question is very important in such situations. He's talking about, already he's terming it as ideal monatomic gas. Okay, so let's underline few things before we start up our journey of the solution. Since it is ideal monatomic gas, we assume by definition that it obeys kinetic theory of gases trapped in the vessel. But even though it's ideal monatomic gas, he is assuming a distribution which is not Maxwellian distribution. This is not how Maxwell's distribution looks like. Okay, so your formula that I have given in the previous slide will not be applicable to this problem, but KTG is still applicable. The KTG part is still applicable. So he says that percentage of molecules which travel with this speed, and there are no other speeds in between. Maxwellian distribution allows almost all the speeds, right from 0 to a very large value. Here this stylish looking distribution only gives certain velocities. It's like a discrete function. So these are the percentage of molecules. large number is there. As we have talked about ideal monatomic gas, large number is there. Temperature of this gas was found to be 324 Kelvin. If all the molecules of the speed, this 800 meter per second, these let's say vanish from the system somehow or removed from the system, is saying what would be the fall in the temperature or rise in the temperature. If you're removing the molecules, you're removing the internal energy. So you should have expected a fall in the temperature. So the decrease by how much value he is talking about. Right. So we should realize one very important thing, that whatever gas molecules are doing, and as they're moving in random directions like this, following this distribution, you recognize that the RMS speed formula root 3 RT by M was the outcome of kinetic theory of gases and not the Maxwell distribution. Even if it is not Maxwellian distribution, your root 3 RT by M formula is going to be correct, assuming all the postulates of KTG, that all directions are equivalent and etc. You cannot use the V average formula that we derived later after the Maxwellian distribution was done, which is that root 8 RT by pi M and all that we cannot use here. Right. And so let me note that particular point here. Ideal gas in the question implies kinetic theory of gases is applicable. Kinetic theory of gases is applicable. That's the first part of the solution, which implies VRMS is equal to root 3 RT by M is correct. That has nothing to do with the Maxwellian distribution. Maxwellian distribution also gives you this formula. You need not always have this only for Maxwellian distribution. That is the something that you need to realize from our previous slides. Not just that, this is not a Maxwellian distribution or Maxwell-Boltzmann distribution. This is something that you should note. So before we move on, let me go back to those previous slides to emphasize what I was trying to tell you. So we already discussed how the Maxwellian distribution or Boltzmann distribution is arrived at. With this slide we have done, and in this particular slide we saw the importance of how distributions come about, right? And I gave you a simple example of Gaussian distribution, how it arrives where balls are falling. And I always love watching this one. So whenever an event happens like this, and imagine I play this again for you. I know I have done that before in the class, but so as the balls start falling into these corners with all the slots there, we saw that a type of distribution of the balls would be centered along the direction of the first point of entry, and you end up getting a Gaussian distribution. So these kind of things give you an idea of how you're supposed to interpret the distributions, and when that distribution is not given, how you should be able to manage in the exam. So that's, so we were looking at this slide just to re-emphasize the kinetic temperature logic and KTG and all that, which reveal the value of root 3 RT by M. By the time we reach this part of the theory, we have not yet discussed the Maxwellian distribution. Then we realize this formula is valid for all gases irrespective of the nature of gas. You don't need a diatomic or triatomic. All of them obey that VRMS square is root that 3 RT by M. Then we decided that okay, let's try to find out how the other molecules are moving, or all the molecules, what kind of speeds they are having, and then we got a distribution function. I gave you reasoning also how these numbers are arrived at, and we match this one with this function. This came first to understand. That means in the ideal gas question that I just now spoke of, in this one I can still use that root 3 RT by M, but I can't use root 8 RT by pi M. So let me go ahead now. How do you arrive at that VRMS square formula? So Imagine I pick all these numbers. Initially, this 800 meter per second set of 20% molecules are also there. So if I try to write the value of the VRMS square, which is equal to 3 RT by M, would have been simultaneously equal to sum of all sets of squares of velocities divided by number of molecules that are there. I can also write it as, let's say n1 number of molecules are traveling with this 100. I would say n1 into 100 square, n1 into 100 square. So something like this would happen, n1 into 100 square plus n2 such molecules are, let's say, traveling with 400 square, and so on and so forth, with the last term of n final multiplied by 1000 square. And then you divide it with, you divide this entire thing with sum of all n's, right? So n1 plus n2 plus so on and so forth. Now think about this. Imagine I write this for T initial. This 3R by M, I don't know, because he's mentioned ideal gas, but he never mentioned the molecular mass. So I have to eliminate that in my answer. We are looking at how to solve this problem without any hiccups in the examination. Okay, right? So my job would be to eliminate this. So if I write T initial, all these numbers would be there because all the contributing parts are there, divided by the sum. So can I now replace this part? Remember this particular part by changing them into number of percentage molecules. So instead of n1 by n1 plus, because I don't know how many molecules are there, I know the percentage. Replace this with this 10 here, and then write the 10 at the bottom, because the ratio will get cancelled. So I would rearrange this as P1, which is P1 is the percentage, and this is P2 and P3, and some of the percentages I'll put at the bottom. I hope you got that point. So this would be associated with, I'll write that 10 into 100 square plus second one would be 20 moving with 400 square, and so on and so forth till the last term, divided by, now instead of n1, n2, n3, you would write 10 plus 20 plus so on and so forth. Now, up till here I think this is very, very clear. So I'll write Ti and Tf, two terms on the left hand side, and I'll divide them so that my 3R by M gets cancelled. But what will I get here? For T final, one term in the numerator and one term in the denominator would be missing. Not only that, since you are anyway going to divide these fractions for Ti and Tf, in the exam, I don't think you should be stretching yourself to solve this actual hundreds of squares and all. Because you are anyway going to divide, I will be smart enough to remove all the extra zeros and replace those numbers for the ratio only. I am not saying it is a correct calculation, it is a smart calculation in the exam. So all the hundreds are removed. For me, this is a 1, 4, 6, 8 and 10, and these are 1, 2, 4, 2 and 1. This is the smart part. Okay, right? So which means if I am doing the T final divided by T initial using this and dividing case 1 and case 2, case 1 and case 2, T final by T initial would be equal to, now let's do the denominator first. It's easy, right? Sum of all these numbers upon divisions would be 100 in the first case and 80 in the second case. And since you are doing second case divided by first case, they are in the denominator. Okay, you would end up getting 100 divided by 80. That would be the ratio of denominators. Now in the numerator, I would be looking at Instead of 10 into 100 square, it would be 1 into 1 square, 2 into 4 square. Those numbers I would be writing. And remember, it is the second case divided by the first case. So in those red colored numbers, I'll write 1 into 1 square plus 2 into 4 square. This is a way to avoid the unnecessary calculation. 4 into 6 square plus the 2 into 8 square is missing, and then last one 1 into 10 square divided by, again I won't write the entire calculation. You see this, that this is the missing number. That missing number will exist in the denominator. So I'll directly write those numbers so that I can be quick with my calculation. So this would be 1 plus this number would be 16 2s 32, then 36 fours is 144. Then that missing number which exists in case 1 would be that 2 into 8 square. 2 into 8 square would be 64 2s 128, that 128 extra, and this would be 100. So all this red colored term now would be nothing but adding all these numbers in the denominator, obviously, and leaving out 128 in the numerator. Simple as that. Because I'm explaining this and solving, it takes so much time. A smart student would be able to do this in a very, very quick manner. And that's what examiner would be hoping for in an objective type paper. So how much would be this? Easier to add 100, then 133, this would be 277. So you'd have a, without 128, you already have a 277. So that would be the numerator, right? So this entire thing would be equal to 10 by 8 is a 5 by 4, that I'll write in yellow. And in the denominator, I ended up getting 277. And you add a 128 to 277, you end up getting a 405. Oh, 277 should be on the top and 405 should be on the bottom. So much so for the fast calculation. Yeah. Okay. Yeah. Student will be anyway faster than me as a teacher. So it's for you. I'm here to provide the methodology of quick calculation. So this would be 5 times of 81, and 81 fours is a 324, which is interesting because in the actual question the value of Ti was given 324. You see this 324, you see, that's what they matched it, which emphasizes the fact that calculation was supposed to be done like this. So with this 324 cancelled with this Ti, Tf would be equal to 277. That's what I would like to talk about. So the value of Tf comes out to be 277 Kelvin, which is a fall from 324. As expected, you remove gaseous molecules contributing towards velocity or internal energy, it cools down. And this ideal gas, which is not obeying Maxwellian distribution but still obeys the root 3 RT by m because it is going to take up kinetic theory of gases. A lot of students make a mistake and in thinking that root 3 RT by m is because of Maxwellian distribution. Yes, Maxwellian distribution gives root 3 RT by m, but we arrive at root 3 RT by m even before going there. That's the most important part. Okay, so that's it. So answer should be decrease by, I think, 47 Kelvin. Decrease by 47 Kelvin or 47 degrees centigrade. Decrease is the same. And which is going to bring us to this part of our assumption. So if I were to, lot of students come up with this particular doubt in this question. Let me make this assumption 1. Assumption 2. So in assumption 1, if we are assuming all molecules are traveling with RMS speed, and in assumption 2, all molecules are traveling with average speed, because first thing that students always want is easier calculation. Average speed is an easier calculation. So the usual mistake that they do is they go back to this distribution, do the average speed, and then they'll get the ratio of average speeds, and ratio of average speeds also would be ratio of square root of 8 RT by pi m. They'll cancel 8 pi's and all that. They'll get a different number here and the answer won't match in the question. Reason is your 8 RT by pi m analysis itself is wrong. Taking all molecules traveling at RMS speed gives you correct energy analysis. It's the easiest way to describe an energy situation inside a gas. Taking all molecules traveling with average speed is not going to satisfy the energy situation, and therefore you cannot use it for the temperature formula. So this is going to match this situation, whereas this one doesn't match this situation. Let me write that so that you can copy it in your notes. Matches with the Maxwellian distribution or that formulae set that we arrive at, whereas this one doesn't match. That's it. Okay, so this is what, it's not just about the solution of the previous Pathfinder question, it's more about what you are learning or extracting the information which supports our previous slides of our class. Okay, right. Okay, I hope you have enjoyed the snippet, and in the end, at the last slide, because I had to cut some part, let me clarify something very important just in case you missed that part of the communication. So when I said assumption 1 where all the particles move with RMS speed is going to match with Maxwellian distribution, I meant the usage of RMS speed for all molecules will match with the energy analysis of Maxwellian distribution. And whereas assumption 2 with all molecules moving with average speed, if you take that assumption, energy analysis of this model will not be able to match. It's not that when you take all molecules to be moving with RMS speed, all these formula will match. Only root 3 RT by m will match. Average speed and most probable speed will also become root 3 RT by m. It's the matching that I talk about in terms of the energy analysis. Okay, right? So like I said, all this content you can find out on the PhysicsSirjee new app, along with the doubts platform app, which is to be downloaded in order to ask your doubts. Please do check out the description and the pinned comment for all the details. Right, like I said, I would be announcing the next problem contest and the details about that. Right, so as I already requested, please make sure you like the video. More the number of likes, more frequent the videos I have already promised. So I'm not going to back out on that promise, and I expect the same kind of love I have been receiving in the past few years. So please do hit that like button. And like I said, I wanted you to comment below about the next problem contest on which topic you would like. I would want both 2025 aspirants and 2024 aspirants to get involved in that problem contest. And one small thing I would like to change with the upcoming problem contest, what I thought I will let you know, so that you can give me an advice in the comment section. Within few days time, depending on the likes for this video, I'll immediately release the problem contest. So what I was thinking was, I will have a combination of 2 chapters at least, so that it's a nice problem which involves mixed concepts, one of them being heat and thermodynamics that I would want to, because that's the ongoing syllabus in the detailed course. Second thing is, I will have parts in the problem wherein each part would be given a percentage of the reward, instead of last 2 problem contests where you are supposed to get that entire solution. A lot of students came very close to getting the reward, but they were slightly disappointed. They understood the rules, they were slightly disappointed that they could not get the reward. So I want more people to be involved in this. So I'm thinking of giving some partial marking, so partial rewards. Right, so please do let me know which topic or whether partial rewards is going to work or not. That's it. I hope you have enjoyed, and also let me know what kind of snippets you want from which type of courses. So any advice which is rational enough, I would be definitely taking up in the video. Thanks for watching this long, and see you in the next video.